The manufacturing process of Xblocs begins with the initial assembly of the formwork. The formwork, along with the end plates, is first assembled. A crane is utilized to suspend and position the formwork components during assembly, enabling accurate alignment and structural integrity. Once the formwork is assembled, the ready-mixed concrete is delivered to the site using a truck agitator. The concrete is then transferred into a red pump truck, strategically positioned for efficient handling. During rainy weather, a rain protection sheet frame is installed to prevent contamination of the concrete by rainwater. This precaution ensures the quality and consistency of the mixture. Concrete is discharged from the pump truck through its tip, maintaining a controlled and clean transfer. Concrete placement into the formwork is executed using the pump truck. The placement process involves pouring the concrete in 4 distinct layers. Each layer is carefully compacted using vibrators to eliminate air bubbles and ensure uniform density. One operator is assigned to each leg of the tetrahedral structure to handle the vibrator, optimizing compaction efficiency. Safety is prioritized during this phase, with workers wearing safety belts, particularly when operating at elevated positions. The upper layers of concrete are poured in the same meticulous manner to maintain structural consistency. Once the concrete reaches the top of the formwork, any excess slurry is carefully removed. This step is crucial to achieving a smooth and clean finish. Before finalizing the top surface, a tool called Picocon is employed to extract residual air bubbles. Using Picocon minimizes surface imperfections, leaving the structure with an even and polished appearance. To prevent rapid surface drying, a curing agent is applied to the top layer. A protective cover is then placed over the concrete to maintain optimal curing conditions. These measures ensure the concrete achieves the necessary strength and durability. Formwork removal. After the concrete has set and cured properly, the formwork is removed. This process is carried out using a crawler crane to safely and efficiently detach the formwork components. With the removal of the formwork, the Xbloc manufacturing process reaches completion, leaving behind a structurally robust and well-finished product. This systematic process guarantees the production of high-quality Xblocs, meeting engineering standards and ensuring reliability in their intended applications. Around the world, more and more breakwaters are being constructed using our innovative Xblocs. BAM Infraconsult, operating under the trade name Delta Marine Consultants, DMC, is the inventor of these X-shaped concrete blocks. Xblocs have already been used in countries such as Costa Rica, Ireland, Poland, Australia, and Benin. In the Netherlands, an Xbloc breakwater has been in place in Kadzan since 2016. Currently, Bouygues is building an Xbloc breakwater in Calais, one of France's most important ports. The blocks are produced fully automatically in a high-tech factory. The manufacturing process of Xblocs is highly automated and designed for precision and efficiency. It begins with raw materials, including aggregates, cement, and water, which are stored and carefully inspected for quality. These materials are then sent to the concrete plant, where they are mixed in exact proportions to create the concrete needed for the Xblocs. Samples of the fresh concrete are analyzed in a laboratory to ensure consistency, strength, and traceability. Once approved, the concrete is poured into molds of various sizes, capable of producing Xblocs ranging from 4 to 14 cubic meters. Each day, between 28 and 40 Xblocs are cast, depending on the project's requirements. After pouring, the molds are transported along a drying line where the concrete hardens. The molds are cleaned and prepared for reuse, ensuring continuous production. The blocks are dried both internally and externally for 2 days before being moved to a temporary storage area using a specialized stacking system. Rigorous quality control checks are conducted to ensure each block meets the specified standards. Once approved, the blocks are transferred to the final storage area, which can accommodate over 1,600 Xblocs. Transporting and placing placing the Xblocs is also carefully planned. Each block is equipped with a gyroscopic unit, known as bib, which monitors its orientation and alignment. An acoustic camera provides real-time feedback, ensuring precise placement and interlocking with adjacent blocks. In total, 16,000 Xblocs will be used to complete the Calais Port 2015 project, providing long-lasting protection against waves and storms and ensuring the port's functionality for decades to come. In June 2012, Sheet Piling UK Limited was invited to tender for the construction of 2 circular cofferdams at the entrance of Great Yarmouth Harbour. The project aimed to install the cofferdams at the outer harbour breakwaters while minimizing disruption to harbour activities and ship movements. The tender conditions required the completion of the cofferdam installation works by the end of August 2012. Given the fast-flowing tidal conditions at the site, Sheet Piling UK Limited adopted an innovative construction method. The approach involved pre-assembling the cofferdams on adjacent quay sites before floating and positioning them in place. This method ensured efficiency and accuracy while addressing the challenges posed by the tidal environment. To execute the plan, a robust, temporary support frame was fabricated and assembled onshore. Straight web sheet piles were carefully interlocked around the frame and secured at the upper level. Monitoring of pile alignment ensured that the circular structure was closed without inducing closure strain. Once assembled, the structure weighed approximately 400 tons. A jacket piling barge was mobilized and positioned at the proposed installation location. A large shear leg crane barge, Smith Tuck Lift 7, was brought in for heavy-duty lifting. 4 heavy-duty lifting straps were connected to the lifting points of the temporary assembly. Using GPS positioning techniques, the pre-assembled cofferdams were carefully lifted from the quay and floated to their precise locations. Upon reaching the designated positions, the cofferdams were lowered accurately onto the seabed. To secure the structures, 8 660mm diameter tubular piles were vibrated 5 meters deep into the seabed, anchoring them firmly in place. The straight web sheet piles were then driven sequentially to the design depth using a crane-suspended vibratory hammer. Once the structures were in position, hydraulic pumps were used to place fill materials into the cofferdams from a land-based stockpile. This step ensured additional stability and strength. The innovative pre-assembly and floating installation method enabled both cofferdams to be installed within a 1-week period without causing any disruption to normal harbor operations. The entire subcontract works were completed by the end of August 2012, meeting the project deadline. This project marked the first time such a method had been used for constructing cellular sheet pile cofferdams in tidal waters within the UK. The 67XXL monopile foundations support 6 megawatts turbines, generating 400 megawatts of electricity, enough to power 400,000 German homes. Scour protection at Veja Mate was installed using the fall pipe vessel Rockpiper. This specialized vessel deployed stone material around the monopile foundations to prevent seabed erosion and ensure long-term stability of the structures. The 67XXL monopiles were designed and fabricated in Rostock, Germany, with dimensions up to 85 meters long and 7.8 meters in diameter, ensuring robust support for the wind turbines in challenging offshore conditions. The monopiles were transported on barges through the Kiel Canal, reaching the feeder port in Eemshaven, Netherlands, for further installation preparations. The installation vessel Skyla was mobilized specifically for the Veja Mate project, equipped with a bespoke 650-ton double-level pile gripper frame. This custom-designed frame enabled the vessel to handle the XXL monopiles in challenging offshore conditions, allowing efficient installation even in higher sea states, ensuring precise and stable foundation placement. The world's largest monopiles, measuring up to 85 meters long, 7.8 meters in diameter, and weighing 1,300 tons, were upended for installation at Veja. The monopiles were driven to target depth using precision equipment, with noise mitigation techniques like the hydro sound damper and double big bubble curtain employed to reduce environmental impact during installation. A survey tool was installed to perform top flange surveys with laser precision, ensuring accurate alignment and positioning of the monopiles, which is crucial for the stability and performance of the wind turbines. The transition pieces and anode cages for the Veja wind farm were transported from Aalborg, Denmark, to the feeder port in Eemshaven, Netherlands. This process involved careful logistics, as the transition pieces, essential for connecting the monopiles to the turbine towers, were large and heavy. Once in Eemshaven, the transition pieces were prepared for installation, while the anode cages were used to prevent corrosion, ensuring the longevity of the offshore structures. Marine growth was removed from the monopile surfaces before installing subsea anode cages, which protect the structures from corrosion over time. The transition pieces were installed by bolting and grouting them onto the monopiles, ensuring secure connections for the turbine towers. Bolting and grouting were used to secure the transition pieces to the monopiles, ensuring stable, long-lasting connections for the turbines. In September 2015, a significant milestone was reached in the construction of the Mersey Gateway Bridge, with a successful concrete pour for the second vertical section of the South Pylon. This event marked a major step in the development of the 125-meter-tall South Pylon, one of the key structural elements of the bridge, which is designed to span the River Mersey and connect the towns of Runcorn and Widnes in the UK. The concrete pour involved an impressive amount of material, with over 1,200 cubic meters of concrete being delivered and poured over the course of several days. This was done using a method known as a climbing formwork system, which allowed for the gradual and controlled construction of the pylon's vertical section. The South Pylon is a critical component of the bridge, as it supports the cables that will carry the weight of the main span and help secure the structure. The pour was carefully planned and executed, with multiple teams involved in ensuring that the concrete set properly, and the formwork system was adjusted as necessary to accommodate the growing height of the pylon. Environmental conditions, such as temperature and weather, were also taken into account to ensure the quality of the concrete and the safety of the operation. This concrete pour was a significant achievement in the overall construction timeline of the Mersey Gateway Bridge, which had begun in 2014 and was scheduled to be completed in 2017. The successful completion of the second vertical section of the South Pylon demonstrated the skill and coordination required for such a complex infrastructure project, bringing the Mersey Gateway Bridge one step closer to becoming a crucial transportation link for the region. Aquafarm Equipment has positioned itself as a global leader in the design and development of advanced, full-scale closed fish cage systems, revolutionizing the aquaculture industry. Among its innovative solutions is the Neptun project, which showcases the world's largest closed fish cage, constructed using glass-reinforced plastic, GRP. This breakthrough design aims to address the growing need for sustainable fish farming, offering a reliable and controlled environment for fish to thrive. The Neptun concept was launched in July 2013 with its pilot system installed on the rugged west coast of Norway, a region known for its harsh yet pristine waters, perfect for testing such a pioneering system. The cage, constructed from GRP, offers remarkable durability and flexibility, providing a robust structure that is resistant to the elements and significantly reducing the risks associated with traditional open sea cages. GRP is a material known for its strength, corrosion resistance, and lightweight properties, making it ideal for large-scale marine applications. The pilot project quickly became a focal point for aquaculture innovation. Extensive testing commenced in the autumn of 2013, with research focused on optimizing several critical parameters. One of the primary goals was to monitor and improve fish health within a controlled environment. Closed systems like Neptun offer superior protection against diseases, parasites, and predators, which are common in open sea cages, thus reducing the need for antibiotics and pesticides and promoting healthier fish stocks. Water quality is another central area of focus. In a closed system, the water can be more easily controlled, allowing for precise adjustments to key factors such as oxygen concentration, temperature, and flow rates. This regulation creates an optimal environment for the fish, improving growth rates and reducing stress. Researchers and engineers have worked tirelessly to optimize these variables, ensuring that the Neptun cage provides the ideal living conditions year-round, regardless of the weather or external water quality conditions. In addition to the biological aspects, the structural integrity of the cage is also under rigorous testing. The mechanical and structural components are continuously evaluated to ensure the system's long-term stability and performance in the harsh marine environment. ADYR Construction is a prominent Israeli construction company known for its expertise in large-scale infrastructure projects. One of its notable undertakings is the Haifa Port Project, a major development aimed at enhancing the capacity and efficiency of the Port of Haifa, one of Israel's busiest and most important maritime gateways. The Haifa Port Project, led by ADYR Construction, focuses on the expansion and modernization of the port's facilities to accommodate larger vessels, increase cargo throughput, and improve operational efficiency. This ambitious project involves the construction of new docks, state-of-the-art cargo handling systems, and advanced logistical infrastructure. It also includes the upgrading of the port's access roads and the implementation of cutting-edge technologies to streamline operations. ADYR's involvement in the Haifa Port Project highlights the company's expertise in complex civil engineering and construction. The project is part of a broader national effort to upgrade Israel's port infrastructure, which is essential for maintaining the country's position as a key player in global trade. A cofferdam is a temporary structure used in marine construction to isolate an area of water, allowing work to be carried out on land. By keeping water out, it creates a dry environment for construction teams to safely work on projects like bridges, piers, docks, or platforms. Cofferdams are typically made from sheet piles supported by internal braces, and their design can be customized based on specific project needs. Once construction is complete, the cofferdam is removed, and the area is refilled with water. The process of installing artificial reefs in Aruba is a key initiative aimed at restoring degraded marine ecosystems in the Caribbean, with a particular focus on coral reefs. This project is part of the EU-funded RESEMBID's Turning the Tide program, which seeks to bolster economic resilience in Aruba through the restoration and conservation of its marine biodiversity. In collaboration with the Aruba National Park Foundation, Wageningen University and Research, and other partners, a detailed restoration plan was developed. Artificial reefs are constructed locally using modular Moses units, which are heavy-based structures designed to mimic natural reef habitats. These units are bolted together with stainless steel fasteners, allowing for community involvement in their assembly. Once constructed, the reefs are transported to the harbor and loaded onto a special installation vessel, equipped with a crane. The reefs are then placed in predetermined locations, some of which are difficult to reach by boat. In these cases, the reefs are initially lowered into safe nearby waters before certified divers use balloons to position them at their final locations. To kickstart coral restoration, cultivated corals from the Scubble Bubbles Foundation will be transplanted onto the artificial reefs. This will help encourage the regrowth of coral populations. The University of Aruba and Veja University will monitor the growth of these corals and track the marine life that adopts the reefs as a habitat.